Hello everyone. So in this particular video, we are going to see this 5 questions that are related to reactive power and you can say improvement of the voltage profile in a power system network. So I will discuss what are the uses of reactive power in AC system, then why reactive power compensation is required in power system. Actually, I made a video on this particular questions in detail. There I have analyzed why reactive power compensation is required. Still, in this video, I will mention few points and what are the various methods to compensate the voltage drop in power systems, and how does the series and shunt compensation works to improve voltage profile in transmission lines, and what are the disadvantages of low power factor in power system. So these are the, you can say, the uh, these questions give you the basic idea how to deal with this type of questions, how to improve the voltage profiles in the power system network, and why there is a need of reactive power compensation and all. So let me start with the first question. Why do we need, what are the uses of reactive power in power systems, even in machines and all, if you see? So basically, in one sentence, if I say, what is the requirement of the reactive power? See, you cannot basically transform the active power without having any reactive power. So I will take few example, then this point will be clear to you. Okay. So let me take example of transformer first. So in transformer, let's say you have a transformer with you, and transformer has a winding. Okay. So if you see the working principle of transformers, basically you have, let's say you have a electrical energy source in the primary side connected. So once you connect a primary source, and then what will happen? This electrical energy, because of this electrical energy, this it will draw a current, that is something we call the exciting current, and it is a AC source basically, Vs of t. And because of this AC source, one exciting current will flow, and a flux will set up in the magnetic core. Okay. And this magnetic flux will induce a voltage at the secondary, and also it will induce a voltage at the primary also. And if you connect a load here, then the energy will given to the this load. Okay. So what is happening here? You are initially you had electrical energy, then you that convert that electrical energy into magnetic energy, because this flux it is a it is a magnetic field, right? And magnetic field you can create with the help of inductor. So and this magnetic field is basically required to to induce a voltage in the primary and secondary sides. Okay. So this magnetic, you can say this electrical energy is getting converted into magnetic energy, and again the magnetic energy getting converted into electrical energy. For time being, if you just neglect the core loss of this particular core, then you can see, if you recall the equivalent circuit diagram of a transformer, in transformer equivalent circuit diagram, if you see the shunt branch parameters, you represent the shunt branch parameter like this, right? So this is your the shunt branch parameters and all, you can say, for a transformer. Now, if you neglect the core loss, this particular component will not be there, but you will be having this inductance that will represent the, you can say, to represent the this inductance of the core. So, and this inductance is associated with the reactive power, and this particular inductor is responsible to maintain the magnetic energy, you can say. Or first this electrical energy is getting converted into magnetic energy, and again the magnetic energy, it is getting converted to electrical energy. If it is a resistive load, that entire electrical energy will consumed in this resistance, if it is a resistance load. Okay. So without having a magnetic energy, or we can say without having any reactive power in the system, you cannot transfer the active power. This is from, you can say, from transformer point of view. If you see the rotating machine point of view, let's say you have a induction motor with you. Let me take an example of induction motor maybe. See, induction motor, if you see the induction motors and all, induction motor at starting the equivalent circuit of induction motor and the you can say the transformers are same. Later on the frequency of the rotor circuit changes, and accordingly that effect can be considered in the equivalent circuits. Okay, but if you see the equivalent circuit of induction motor also, like uh, like the per phase equivalent circuit diagram, you will see you have this sort of equivalent circuit diagram. In case of induction motor, this core loss, also this magnetizing inductance is huge because of the air gap in the system. Okay, so you have this sort of equivalent circuit diagram, and this particular inductance is associated with the reactive power, and this inductor actually maintain the flux around the air gap, you can say. So here also we need, like, you are having electrical energy coming from the source, electrical energy, and that some amount of energy will consumed in this winding resistance and the leakage reactance, this amount of flux will not able to link the secondary circuit or the rotor circuit, you can say. And this inductance is basically representing the magnetizing inductance that will set up the flux, or we can say this will like behave as a reactive power source. You will reactive this sorry, not a source, but it will behave as a sink of reactive power, you can say. And this inductor will maintain the flux in the air gap. So this particular part is responsible for the magnetic energy or reactive power portion, you can say, reactive power. And again, this from this and reactive power is associated with the magnetic energy, and this magnetic energy again converted into the you can say the rotational energy. Okay, because this is the mechanical load represented in the electrical domain, which is nothing but R2 1 minus S by S. So you are having electrical energy, then you convert it into magnetic energy, then that magnetic energy getting into rotational or mechanical energy. So this is the part of induction motor. If you see from the DC machine point of view, in case of DC machine, if you see, let's say you have a uh, shunt DC generator with you. Okay, okay, and it is EG, it is RA, it is RF. If you see the voltage build-up process of shunt DC generator, uh, it is something like, it is start like that, and this is the EF voltage, and this is my field resistance graph. Okay, and initially if you don't have any kind of residual flux, this amount of flux, this amount of voltage is because of residual voltage. So initially this magnetic circuit or the field circuit will have some residual voltage. If you keep on increasing the voltages and all, and you keep on increasing the speed of the you can say the generator, then what will happen, because of the field this amount of this you can say, because of the residual flux, this amount of voltage will induce, and that voltage will lead to field current. You can say the field current, and you will get some amount of field current here, and that field current will enhance the field excitation. Okay, so that will increase the field excitation voltage, and slowly you will get the voltage build up process. You can study in depth like how the voltage build up happens in case of DC generator, shunt generator. So basically you need reactive power to set up the you can say to set up the voltage, or to have a voltage build up in a DC generators and all, you need reactive power, because this field circuit is associated with the reactive power. And we need this particular thing to for the voltage build up process, such that if we connect a load after some time, we should be able to supply the power to the load. Okay, even same thing happens with the synchronous motor and alternator. Like if you don't give any kind of excitation, if you see the synchronous generator, uh, Let me take one example. Let's say, just roughly I'm drawing it. So let's say this is my A phase only. Just I'm drawing A phase only. And if you have a, let's say, rotor, okay, if you don't give any kind of excitation in the circuit, okay, if you don't give any kind of excitation in the circuit, and let's say your alternator is operating at isolated conditions, so if you don't give any kind of excitation in the circuit, you will not get any kind of voltage induced in the A dash coils. But if it is connected to infinite bus bar, then even if you don't give any kind of field excitation, it will draw a lagging current from the grid, and it will set off a flux, or that will create environment to transform the power. But in case of isolated case, when the alternator is operating at isolated condition, you must have a field circuit. And once you have the field circuit, that will create you can say an environment that will produce a reactive power. That reactive power is required to get the induced voltage in this A dash coil. Then you can get the power output. So in alternator, first you have mechanical energy, you can say, then magnetic energy. And magnetic energy is nothing but the reactive power in this case, in the form of reactive power. Then the magnetic energy getting converted into electrical energy. So this is how, like, without having any field excitation circuits or reactive powers and all, you cannot even transform any kind of active power. So that's why we need this particular thing, like the uses of reactive power. This is very much essential, like to have a reactive power. If we don't have any reactive power in the system, then it will be like it is not a good scenario for us. Okay. Now, why is reactive power compensation is required? First of all, why there is a reactive power compensation required? So basically, reactive power compensation and the voltage, these two things are tightly coupled. Okay, so let me take one example for that. Then it will be much more clear for you. Let's say you have two bus system, and this is Vs at an delta, sending end voltage, and Vr at an angle 0, and Jx. So if you calculate the what is the reactive power that is getting supplied at this receiving end. So first let me consider the current, or like if we calculate the current, that will be Vs at a delta, at an angle delta, Vr at an angle 0, Jx. So Vs x delta minus 90 minus Br by x minus 90. Okay. Now if you see the complex power at the receiving end, Vr at an angle 0, Vs x delta minus 90 minus Vr by x minus 90 degree, and obviously conjugate, right? So you will get Vr Vs by x at an angle of 90 minus delta minus Vr square by x 90. So if you calculate the reactive power at the receiving end, Vr Vs by x sine 90 minus delta, I am just considering the reactive power, so that will be cos delta minus Vr square by x. Sine delta is 1, so it will be no issue. So that will be 1. So now take the common Vr by x. So Vs cos delta minus Vr. Okay. So the receiving end reactive power, you can see you are having this particular thing. Basically, at generally this delta rotor angle, or you can say if the generator is connected at this terminal, this rotor angle varies. Generally we try to keep this rotor angle towards the lower side. So just for analysis purpose, I am considering this rotor angle tends to 0, but it is actually not the case. But for the better approximation, I am considering the rotor angle as tends to 0. So my cos delta tends to 1. So from this particular equation, I can say the reactive power at the receiving end is basically Vr by x and Vs minus Vr. Okay. And I'm calling this particular term Vs by minus Vr as a delta V. So I have QR is equals to Vr by x delta V. Okay. So what is the delta V? Delta V, it is nothing but the voltage drop. You can say at here I have this voltage drop. Okay. So delta V is equals to QR x by Vr. So this is the thing that that is required for us. And from here also you can see the reactive power flows from, like, if this reactive power QR will be greater than 0, this QR will be greater than 0 if Vs is greater than Vr magnitude only. So to have reactive power flow from source to receiving end, you must have sending end voltage more than the receiving end voltage. Then only you will be having more reactive power flow from sending end to receiving end. Okay. And also, see, the voltage drop is kind of related to the receiving end reactive power. If you have less amount of reactive power at the receiving end, that means you have less amount of reactive the voltage drop in the transmission lines. Approximately, you can say it is not exact, but approximately this is how it is related. So our goal should be like the receiving end reactive power, we should be able to deliver the reactive power to the load. Let's say we have some load connected here, some inductive loads and all it is connected here. So we must have some device that can supply reactive power locally, like let's say some kind of compensating device must have that will supply the reactive power locally. And we need not to deliver the reactive power from the source end, or else this drop will increase so high. So we have to avoid that scenario. So this is the case, like reactive power and voltage drop, they are tightly coupled. And the question was, why reactive power compensation is required? Because if you don't provide any kind of compensations, let's say you have this Vs at an angle delta, Jx Vr at an angle 0, and you have some amount of heavily inductive load. If you don't connect any kind of local capacitors and all, then what will happen? The receiving and reactive power will directly come from the source side. Okay, the receiving and reactive power will directly come from the source side, and the voltage drop here it will be huge, and you will be having like poor voltage regulations and all. Okay, so that is not a good scenario. But if you connect a capacitor here to supply the reactive power to this load, then what will happen? This reactive power demand, or you can say that this receiving and reactive power will drastically reduce. This QR will drastically reduce because I need not to supply reactive power from the source, but my capacitor will supply reactive power to this RL load, and this reactive power QR will simply reduce, and therefore my voltage drop will also simply reduce. So I'll be having much good voltage at this receiving end. So that's why I need this reactive power compensation. This is about the shunt compensating device. We have also series compensating devices and all that I will discuss in the next questions and all. But I hope it is clear. Like if you have this compensating device, you will be having less drop, and also by having the reactive power compensating device, you can get good voltage. You can say good power factor. The power factor that you will get at the receiving end, it will be very good. Because the moment you have improved power factor, that means you can able to supply more amount of active power. I hope it is clear. Okay, so it basically improve the power factor and it improve the voltage regulation, you can say. This reactive power compensation. Okay, like let's say this RL load was basically it was around 0.4 power factor lagging, but you want to improve it to, let's say, 0.9 power factor. Then you must connect a capacitor. That's how it can basically improve the power factor. So these are the main things and all. And also, once you have this compensating device, then basically you need not to transform the reactive power from the source. If you consider on resistance here, then to have some amount of some good amount of reactive power from source to receiving end, the current in the circuit or in the line will also increase. But in that this magnitude of current will be very high, because if there is no reactive power compensating device, this current can lead to more losses in the transmission line. So it also reduces the losses in the transmission line. So these are the main points: improve the power factor, voltage regulation improve, and losses in the transmission line also reduces. Okay, yeah, these are the points. And what are the various methods to compensate the voltage drop in power system? See, basically you can have various methods. Like if you have a, let's say, synchronous generator, you have inductive reactance lines, and you have some load here. Okay, because of this inductive reactance, you are having more line drop here. But if you connect a series capacitor, it has Jx inductive reactance, and but here the capacitor will provide Jxc inductive reactance. So effective inductive reactance will simply reduce to X minus Xc, and the since the inductive reactance is reducing, the voltage drop will also reduce. Also, you can think from that point of view, like if you know the voltage per unit voltage regulation is nothing but RPU cos phi, the load power factor, plus X per unit sin phi. So this is the voltage regulations for inductive load. If you reduce this X per unit, because generally R per unit is very less, but X per unit is this line reactance is very high. But if you reduce this X per unit, your voltage regulation will also improve. Okay, so by using series capacitor, you can improve the voltage profile. And also you can, if you think from the load circuit point of view, let's say you have inductive load connected here, you can connect a shunt capacitor to supply the reactive power that will improve the power factor, that will reduce the transmission line losses, and you can say that will improve the voltage regulations and all. Okay, so you can either connect capacitor, you can either connect a synchronous condenser. Synchronous condenser is basically a motor, synchronous motor that is operating in overexcited conditions, that will supply reactive power to this load. And also you can use some other devices, something called statcoms and all of these things you can connect as shunt to improve the this you can say voltage profile and all, or also you can reduce the voltage drop in transmission lines. Also you can use the tap changing transformers. Let's say you have two winding transformers, and you have like step up voltage transformer, and you are taking several taps. So depending on, let's say this is your transmission lines, this is your inductive load, and the tap was initially connected here, but because of the heavy inductive load you're getting much more drop here. So rather you can just move the tapping point to some this point, increase that number of turns ratio, that will improve the voltage at this point, and also it will be able to deliver the active power. So by having the tap changing transformer also, you can improve the voltage regulation and all. So these are the main things that are, you can say, improve the voltage, uh, voltage drops in the power system. How does the now, fourth one is the how does the series and shunt compensation works to improve the voltage? Well, that I have already discussed. And what are the advantages of disadvantages of the low power factor? See, basically the power factor I'm considering. Let's say, let me explaining here itself. Power factor is nothing but active power by apparent power. Okay. Now, you can have low power factor. There can be two scenarios. Okay. First of all, if you have a lagging load, let's say if you have lagging load, in that case, the power factor will be poor at the receiving end. Okay. So to improve the power factor, if you have poor power factor, let's say if it is a heavily lagging load, I'm considering lagging load only because in practical we have only RL load, but you can take the RL, RC, those type of load also. But in general we have RL loads. So if you have this lagging load, in one of the videos I have explained, like because of a lagging load, let's say if you have synchronous generator here with you, you have inductance, line inductance, and if you have just let's say purely inductive load, if you have, in that case I have analyzed, like there will be much deep like in the voltage, so the voltage drop at the terminal voltage will be something like that. So if at no load, if the terminal voltage EF, as you increase the current, the terminal voltage will simply reduce. That means you are having much voltage drop here, and this is for ZPF lag load, purely inductive load, ZPF lag load. But if you consider some 0.95 or something like that, so it will be not a linear, but somewhat this kind of voltage, terminal voltage graph you will get. Okay, some kind of voltage drop you will get, voltage that terminal voltage profile you will get. See, in this case what is happening, as you increasing the more as you are drawing the more lagging current, the load is more drawing the more lagging current, the terminal voltage is simply reducing. what is happening because of that? Your line current is simply increasing because it is you are drawing more lagging current, so line losses will simply increase. So line loss will simply increase, and you you are getting much more voltage drop in the transmission line. So voltage drop will also increasing in that case, and you can say this is not a good scenario. So we must have a reactive power compensating device to improve the power factor. So because of low power factor means it either it is highly lagging load or highly capacitive load. I'm considering only lagging load. So in case of highly lagging load, you are having you can say the voltage at a terminal is simply dropping. There is much voltage drop in the transmission line. There is much more losses in the transmission line. Or also, if you have less power factor, that means your active power delivery is also simply reducing. So that means you are not even like you are not supplying more active power. So if you see from the generation point of view, if your power factor is too low, that means you are not even supplying more active power, so you'll not get much profit from that. So we need to improve the power factor by connecting a capacitor. You can connect a shunt capacitor. You can choose either condensing synchronous condenser, then the capacitor bank, and all of these things, okay, to improve the power factor. There is one more scenario that can lead to low power factor, so that is because of harmonics. See, harmonics, like if you consider a rectifier, let's say if you have a rectifier and the rectifier is feeding a constant current load, okay. If you see in this case what will happen, let's say this is your supply voltage Vs of t, but the source current Is of t, it will not be sinusoid, it will be like square wave in nature, right? And like that. So and it is I naught, okay. See, the source current is not a purely sine wave, it has lots of harmonic associated with it. But since my source is purely sine wave, the active power from the source will because of the fundamental component of this I naught. That is nothing but, if you see the fundamental component of the source current, 4 I naught by pi sine omega naught t. So this is the fundamental component, and you will get the power because of the fundamental component. But here we have the harmonic component also. So if I write the Fourier series expression, it has triple harmonic, odd harmonics, 4 I naught by n pi sine n omega naught. So you can see there is third harmonic, fifth harmonic, all this component is there, and you are having active power delivery because of fundamental component of current, but there is apparent power. The apparent power is nothing but, let me write down the active power first. P is nothing but uh, let's say my supply voltage is something, let's say VST is some root 2 Vm root 2 V sine omega t omega naught t, let's say. So my active power will simply be V into 4 I by pi root 2. This is my active power, but my apparent power will be V into I naught, okay. So if you take the ratio, you will get the power factor of the system, but here you will see the power factor is much less. So and so so to improve this power factor, you either you have to connect some statcom to supply this harmonic current, or else what will happen, let's say you have this particular load connected at this bus, and here you are having stable sinusoidal voltage, and you have this non-linear load. Let's say you have this non-linear rectifier load, okay, and you have some transmission line, you have this another bus. So if I consider this voltage Vs is purely sine wave, but because of this non-linear load, this current is also non-linear. So the voltage that you will get here Vs dash. So Vs dash is simply nothing but Vs plus, let's say this is my Z into Is of t. Obviously Z will vary depending on the input current frequency, but you can see the effect of the non-linear current is also affecting the Vs terminal voltage, this voltage. So if I have some another load connected over here, say any RL type of load, the performance of this load will also simply like it will deteriorate. Okay, so because of non-linear load, I am getting some kind of non-sinusoidal voltage in the buses that are connected, or that are in the vicinity of this particular bus. So this bus voltage will also like impacted because of the non-linear load. So and if any other load are connected all on other buses, then the performance will also like that it will like impact the performance of those loaded. So we have to consider the effect of this type of effect also. Like if you have this non-linear load which that demand harmonic current, so we have to supply that harmonic current from some external source. That can be some any kind of power electronic circuitry. We generally we use statcom to supply these harmonic currents. Okay, that will improve the voltage profile in all of the buses, you can say. Yeah, these are the questions that I wanted to discuss. Still, if you have any doubt, you can ask me in the chat box. Thank you.